Welcome to our webcast, IIoT Webcast 3, Integration Considerations. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of CFE Media. I'm now happy to introduce today's distinguished speakers, Mike Richmond and Alan Mike Peters. Mike Richmond is Executive Director of the Open Interconnect Consortium, a group of 100 organizations creating cloud-native software standards for the Internet of Things. He has 15 years' experience in open source software and, at a major chip manufacturer, led efforts in web technologies and HTML5, participated in expansion of Ethernet to 100 megabits per second, and managed board and operating system products. He also advanced the computer architecture at a mini-computer company with a strong presence in industrial automation. Alan Mike Peters is Manager Business Development at M2M Access, a division of Onyx Engineering. M2M Access specializes in systems integration and custom solution builds within the Internet of Things space. He has helped numerous companies adopt technologies that positively influence bottom lines and help maintain or expand market share. He developed an economic development strategy for Ontario's largest natural gas utility and managed that program for 5 years before venturing into the private sector. I'm Mark Hosky, webcast moderator and content manager for Control Engineering. And now we'll move on to Mike Richmond's presentation.
All right, thanks everybody for joining us today. I'm going to begin the discussion of integration considerations by focusing on three topics. One is to understand why Ethernet, which has been around since the early 80s, was originally viewed as unsuitable for industrial network and yet is emerging as a key to the industrial Internet of Things. We're also going to jump up into the software stack and talk about how some of the software technologies used to provide commercial cloud services that you use on your phones or your tablets, your PCs every day, are actually influencing how we construct industrial applications in a way that provides for reliability, security, and scalability. And then we're going to actually talk about the people who write these things, the actual software engineers, because the environment has changed and the people that you normally associate with building embedded designs or industrial design are in very short supply, and we're going to be drafting people from the mobile world to help us out and to build these new applications. So here we have three seemingly unrelated technologies. Ethernet, both the physical and logical network technology that's implied by Ethernet. Cloud software technologies, and I'm going to focus on two of them, containers, so-called software containers, and virtualization as being very, very important to the industrial Internet of Things. And then the programming language that's used by mobile developers everywhere, JavaScript, and a new platform you may not have heard of called Node.js, which is revolutionizing server-side programming and is also making its way into client-side embedded programming, despite its origins as a web programming language. We're going to talk about all these three technologies and how they're crossing over in ways that might have been unexpected just a couple of years ago. Andy Bechtolsheim is a co-founder of Sun Microsystems, a classic Silicon Valley billionaire, and he now invests in a lot of startups. And he's quoted as saying years ago that Ethernet always wins. Sun Microsystems, of course, was the workstation company that used Ethernet, Unix, and the graphical display workstation to really revolutionize how technical computing was done. And he observed, even at that time, which would have been, now 15, 20 years ago, that Ethernet always wins. And now, of course, if you Google the phrase, the Internet always wins, you'll find all kinds of examples where things that happen on the Internet end up influencing both technical change in other areas as well as, social movements and that sort of thing. So, and the question in both cases is, why is this true? Why do these things tend to win? Why do these things win? And how does that impact the kind of work we're trying to do in industry. So the reason that Ethernet wins is the same reason that any kind of network effect technology wins. It's basically a positive feedback loop. The more investment that goes into a product, the more adoption you get, the more it tends to reinforce the need, the possibility of even more investment. And as we're going to see in a specific example of Ethernet, this positive feedback loop has allowed the purveyors or the suppliers of Ethernet technology to adapt it to scenarios that were never contemplated when the technology was originally invented. So Ethernet has benefited from that from the beginning, from the early 1980s up to now. So we're now talking about 30 or more years of evolution. And as a result, the Ethernet of today is not your father's Ethernet. Now, so let's go back to Ethernet in the early 1980s. As you can see from my picture, I'm a pretty old guy. I'm actually 62 years old. So I remember when Ethernet was introduced, and I remember the promises that were made. I remember how it works. I remember how you put it together, and it was really thick yellow cable, coaxial cable, with little box taps that you would literally screw into the cable and would hang from the ceiling, and then there was a drop cable that went to your computer. And it was a single coax that connected the entire network that could go. It could be as long as 100 meters before it needed some kind of a repeater or some other kind of device in the middle. It was the speed was 10 megabits per second, and that cable was a shared medium. And it worked by the principle that every station, every computer on that network could broadcast a packet at the same time, and if they collided, then each computer would back off a random amount of time and try again. So the protocol was called collision sense multiple access collision detection, and as a result, you couldn't guarantee any particular response time, though in practice, response time was really good. It's a terrific protocol, but when industrial people looked at it, they said, no way, this is never going to fly in real time because there's no way to guarantee that, if that bolt of steel is headed towards the wall, that the message to stop the steel mill is going to get there in time. And so there it sat. It became very, very popular in the office. But if you look at then versus now, what you find is from that thick coax, we went to thinner coax, then the twisted pair copper. Now we have fiber optic Ethernet. We're up to speeds of 1 gigabit per second. We're now up to 10-kilometer distances with fiber. We can have switch topology, so you don't have to worry about the collisions anymore. Each station is effectively on its own wire. And now there's even a new standard that is gigabit Ethernet adapted to industrial applications and the automotive environment. And the only reason this is possible is that the return on investment from the early applications is feeding the investment in the new application. The key to the longevity of Ethernet as a standard in the presence of all this investment is backward compatibility. So you can take one of the oldest Ethernets out there and bridge it with readily available equipment to the Ethernet gear you can buy today. And this is actually an astonishing track record of compatibility over the decades. In addition, because Ethernet was invented as a shared network where you could have multiple computers literally on the same wire, it was architected assuming that those computers might be running different networking software protocols, and they're unaware of each other's traffic. And so that's yet another way that compatibility has been maintained, because if you had an old Ethernet that was using old protocols like Novell NetWare or the original IBM PC networking, and now you put the same set of you put all that traffic on the same Ethernet as something running TCP/IP or a newer protocol. They don't collide with, they don't get in each other's way. And again, this is is a great property in the industrial world where you may have installed networks that live for many, many years. You may not know this, but Wi-Fi, the 802.11 standard that we use in our homes all the time, is essentially wireless Ethernet. So the underlying physical protocol is completely different. Obviously, it's wired versus wireless. But the packet formats and those kinds of things are basically the same. And so that you can bridge from a wireless network to wired very easily. And when you talk about going from one network to another, the cheapest thing is just being able to plug one cable into another. If you have live electronics between the two, but they don't have to do very much, that's a bridge. If you have to do some kind of change from one transport protocol to another, that's called routing. And then above that, you're usually looking at application-level gateways. So the fact that we can bridge is actually really nice, especially within a particular facility. Once you go outside a particular facility's wall, you probably should be using a router anyway. So the nice thing about Ethernet is this backward compatibility, and you can upgrade or adapt to a new technology without having to change the software that runs on top of Ethernet. Now, typically, on top of Ethernet, you're going to see today TCP/IP. This is its own standards battle. This is what's running on the Internet, or this is what runs the Internet. It is so popular, it actually ran out of address space everywhere except Africa. So now we have a new version of TCP/IP called IPv6. Gives us a huge increase in address space. You can route from IPv4 to IPv6. Of course, both can coexist on the same Ethernet or Wi-Fi network. One cool IPv6 fact, if you're only used to running IPv4 in your home, you may notice that the IP addresses in your home are generated by your router. But IPv6 IP addresses can actually be synthesized using the Ethernet device address, or the MAC address, Media Access Control address. And that allows for self-organizing networks, for example, Thread. So you don't even have to be connected to the Internet for a local IPv6 network to organize itself. TCP/IP is one of those things that was designed for local area networks and then longer distance networks like the ARPANET. But now, and it competed with things like asynchronous transfer mode. It came from carriers and so on. Now these things have totally merged in that you see TCP/IP packets get encapsulated for long distance carrier transport, and then unencapsulated, and now it's back to TCP/IP in a local facility. The idea of a virtual private network where your packets are scrambled and encrypted, but by the time you see them, they're unencrypted again. Again, when you have a standard like this that's so durable, it gets adapted and improved in ways that the original authors would have never expected. So there we have that first example of crossover technologies on the networking side, Ethernet and TCP/IP. Okay, let's move on to cloud software. Now, the basic problem when you think about using anything from the commercial world in the industrial world is that, for all intents and purposes, commercial computing rots. And what I mean by that is, if you don't touch it and you don't maintain it and you don't upgrade it, it eventually becomes useless. All right? So we're all familiar with this phenomenon in our personal lives, right? And if you watch the IT departments of the world, the commercial computing gear you can buy today, it isn't designed to last a long time, right? I mean, you buy if the hardware breaks, you can't get spare parts, right? So just as a hint, if you're using commercial computing gear, about the most durable thing about it is universal serial bus. Okay, great. So you pick something with USB, that's probably going to be something that you can count on for a while on the hardware side. But back to software, operating systems, they get upgraded, and that breaks the applications. The economics change. It turns out that instead of buying one big central computer, you should have lots of small computers. And then it turns out you should have cloud computers. And these things change over time. But the most important thing about commercial computing that causes it to rot is security. Because if you don't have the ability to patch and upgrade the software that's running in a commercial application, it will become worse than useless after a relatively short amount of time. As little as 2 weeks and maybe as long as 2 or 3 years, you can basically render whatever you're running completely unsuitable for connecting directly to a network, given all the threats that are out there. So that's the context of the problem that I think we should be thinking about when we look at commercial software technologies. So the cloud can help. All right. So with cloud computing, we have 2 kinds of things. We have virtualization, where you take a complete workload, including the OS, and you package it in what's called a virtual machine, and you ship it off to a server that's shared with other people's VMs, or even another company's VMs, another from a cloud service provider, where you actually essentially rent time. And it helps this problem of rotting software because the OS in the VM is allowed to be much older than the OS that's actually running the hardware. And so the OS running the hardware can have all the security patches applied and so on, whereas you get a little more slack cut for you in the OS and the VM. Not that you don't want to update it, but it doesn't become the kind of thing that can take down the entire application suite that's running on that single piece of hardware. So you're getting the benefits of that hardware, you're keeping it up to date, and if one VM gets compromised, you haven't brought down the whole system. And of course, what's nice about virtualization is if your hardware policy is to buy Windows machines, you can buy Windows machines. If it's to buy Linux machines, you can buy Linux machines. Okay. The other kind of cloud software technology that helps is called the software container. And here what happens is we split the workload into small components, each of which is packaged with the libraries needed to run it, but without the actual OS. So we only have a dependency on a particular library as opposed to the entire operating system. That makes us a little more upgrade-proof. And these containers are only designed to run as long as a particular transaction, which is a huge reliability advantage. And you can run huge numbers of them on a single server or on a VM. Now, what helps here is that the software libraries in a container can be different than can be of a different version than those in other containers, and they're independent of the host OS. So instead of, let's say, sharing a graphics library or a database library with a bunch of other applications, you basically package the application with its own libraries, and that makes it more future-proof and less dependent on revs and things like that. If you go to an IT conference today, all people want to talk about is virtualization and containers. Okay, it's a huge, huge topic. But the fact is that these technologies are are helping on the commercial side are also going to help on the industrial side because they help future-proof what you're doing. Okay, if you're with me so far, let's go drop into the world of the programmers that you actually want to hire to do all this work. And let's talk about JavaScript and Node.js technologies. The data I have here, the statement, embedded developers will have a relatively small role to play in IoT, comes from the company ARM, which is the CPU architecture company that is a part of just billions and billions of devices. Most phones are running on ARM devices, both iPhones and Android phones. There are a few Intel-based devices out there, but most of them are based on ARM. And basically, and they're moving into the Internet of Things in a big way, whether they're sensor networks or anything you like. So they're one of the fundamental engine suppliers for IoT, along with Intel. And what they're basically saying is, hey, there are about 600,000 embedded developers out there, people that know how to do things with real-time OSs, that maybe have EE degrees or computer science degrees with a hardware class. And there's $1.5 billion going into IoT startups. There aren't enough of these guys going to go around. Okay, there just aren't. We can't train them fast enough. On the other hand, there are 8 million web developers and 9 million mobile app developers. And those men and women are also looking for jobs. So how do we bridge, that availability of talent to the economic need that you're going to have of actually creating these applications? Okay. Is there a way to use JavaScript, which all these mobile people know? Your kids probably know it. Maybe even you know it if you've done some web programming. Is there a way to make it applicable for IoT? So let me just give you a couple of observations on JavaScript. It was invented to implement responses to user inputs on web pages. So you fill in a form, you put in an address, you put in your credit card, all that's JavaScript. Millions of people know it. The web would not be interactive without it, but most professional software engineers think it's a toy language. Okay? Now, that's because it has very loose syntax. It's not strongly typed, doesn't have a lot of error checking, and it's not built with, and as a result, it's not really suited for large-scale programming. And yet, on the server side of the world, it has taken the world by storm. It's one of the most popular programming languages for doing server-side programming, and it's becoming increasingly popular for IoT. And the question is, why? How is this possible? And the answer is a platform called Node.js. Now, what Node.js does is take the JavaScript engine that's inside your browser, and it connects it to a non-blocking I/O subsystem that allows for plugins that are written in C. So now you can have interfaces to lots of back-end software on a server, or in the case of a robot, it can talk to a robot arm. And so you have to have somebody that is specialized in the C programming to do the device or server-side stuff, the detailed back-end stuff, but all the business apps, all the business logic can be written in JavaScript. And oh, by the way, this technology also runs on either Linux or Windows. The Node.js is the platform that makes JavaScript programming for us possible in these applications. And the key to this unlikely marriage is architecting the solution to be composed of multiple small services using what's called RESTful APIs. RESTful means that they're stateless. The ST in REST is stateless. And so you don't let any one program get too big. Now, so that solves the large-scale programming objection. The non-blocking I/O means that you can have multiple transactions in parallel, and because the I/O doesn't block, you can use the model in JavaScript that it's actually very well suited for, which is you have an event in JavaScript, and when it's done, you call it back. This is what keeps your web forms from locking up when you program. And so that kind of asynchronous programming is actually exactly what we need when we're talking about devices. Okay, so it's ironic that the technologies that were built for basically web forms and handling human input can actually be adapted to both the back-end services and also to our industrial devices if they're the normal of normal kinds of speed. So the way you exploit this insight is by using Node.js for the cloud side of your solution. There's undoubtedly somebody in your IT department who either knows how to do this or wants to, and then you hire that embedded specialist to go talk to the actual board interfaces. They're the C programmers, and they create a little plug-in, and now your JavaScript guy can talk to both the cloud guy and the device on the end embedded design, and they can talk end-to-end, right? They can write the code end-to-end based on the fact that they're isolated from the underlying hardware by these C-based plugins. Okay. All right. So what I'm trying to explain to you from the cloud with the lessons to learn is you either learn to surf or get drowned by the wave. And what do I mean by that? You can't sit around and say, I'm going to build an application with IoT, and I'm going to lock it down, and nobody's going to change it, and that's how I'm going to solve this problem of software rot. And I'm here to tell you that even if your business requirements don't push you to change and be adaptable, security challenges will push you to be adaptable. All of the examples that I have given you today benefit from irresistible network effects. If there's a missing feature, it'll get added. If there's some objection to be overcome, the investment will be there. And the traditional model of enterprise software from the 1990s is never going to scale to handle the number and kinds of devices that you guys are talking about having in industry. It couldn't even scale to handle the $500 phones that are out there. All this cloud technology was invented in the transition from PC computing to mobile and cloud computing. Okay, so to wrap my section up, network effect economics have enabled Ethernet to help IoT despite where it started. Cloud software enables agility, and you have to have agility because security, well, stuff happens. And it also handles scale. And if you intend to be successful, you will have a scale problem. You'll have millions of devices or hundreds of thousands of devices. And as someone famously or infamously said, you have to go with the army you have, or in this case, the army you can hire, versus the one you wish that you had. And by savvy mix of both can get the job done using Node.js and JavaScript. And with that, I'll turn it back to Mark.
Great. Thanks very much, Mike. That was a fine presentation. Mike had some additional references here. And then here's his contact information. Of course, you can download the presentation anytime as we're going. And then at the end, we'll also have the contact information up as well. So now we move on to Mike Peters' presentation. Mike?
Yes, good afternoon. Hello, webcast participants. As Mark mentioned, I'm Mike Peters, and I'm from M2M Access, which is a division of Onyx Engineering. The objectives presented on this slide build upon the 4 original objectives I was asked to address. In a nutshell, my presentation is less technical and more so informational in focus. Okay, let's begin by defining the industrial internet. Let's start first by exploring the original term, the Internet of Things. The phrase was coined in 1999 by British entrepreneur Kevin Ashton. Ashton was a co-founder of the Auto ID Center at MIT. His center is credited with creating a global standard system for radio frequency identification, or RFID, a term I'm sure most of you are aware of. Today, IoT has grown beyond RFID and RFID tags. It's now more broadly defined as the Internet-connected network of physical objects or things. But in this instance, the things are embedded with electronics, software, network connectivity, and sensors or switches that enable them to collect and exchange data via the Internet. For example, a simple on or off switch you can activate from your phone. The graphic here describes the basic principles behind IoT from the perspective of a consumer's kitchen. From your handheld Internet-connected device, you can transmit information or commands between yourself and your coffee pot, your microwave, your dishwasher, or your stove, even your refrigerator. Not sure why anyone needs to talk to the refrigerator, but that technology is being put in place as we speak. I'm going to throw a curveball out here and state that the first step towards making sense out of all the acronyms that exist in this space is to introduce a new one. And that acronym is the Internet of Everything. For me, it makes sense to start with everything and work backwards. Cisco Systems and Gardner Research introduced the term in 2011. Today, it's largely accepted that IoE is the network connection of people, processes, data, and things. It's all-encompassing. It's everything. But by contrast, IoT refers to the networked connection of just things and does not include people or processes. There exists a whole library of research papers, forecasts, and studies that estimate today's device count and what the future looks like. In fact, there's probably one being released as I speak. I reviewed a number of these and have in this slide depicted the results of 5 that are most often cited. I feel comfortable in going out on a limb and stating that today there are 14 billion IoE devices in existence, and that market will grow to 50 billion by 2020. Here's a mind-boggling statistics for you. Cisco estimates that 99.4% of all physical objects in this world that could one day be part of the Internet of Everything remain unconnected. That's less than 1% of total conceivable connectivity. If 1% is 14 billion, then 100% is 1.4 trillion potential connected devices. This slide breaks down those 14 billion connected devices into 3 separate categories. They're namely smart devices, consumer things, and industrial things. Roughly speaking, there are 7 billion smart devices out there today. That's one for every man, woman, and child on the planet. This segment is expected to grow to 21 billion by 2020. There's an additional 6 billion consumer devices out there as well, and this will forecast to also reach 21 billion by 2020. And finally, the space we're interested in, the industrial space, there's 1 billion industrial things out there today, and this segment is forecasted to grow to 8 billion. We are all familiar with smart devices. They're the portable, wireless, internet-connected phones, tablets, laptops we all use daily at work, rest, or play. Smart devices are not prejudiced. They will serve both consumer and industrial markets, and as their feature sets and capabilities continue to expand and their costs continue to decline, it is likely that each of us will have 3 of them at our disposal by 2020. I suspect that many of you have already reached that total. I know I have. Beyond smart devices, IoT is increasingly being split into the consumer and industrial segments. As you can see in this graphic, consumer will grow the fastest or add the majority of new devices. It represents 85% currently. But the industrial sector will actually grow the fastest. It's forecast to grow from 1 billion to 8 billion, or at 800%. Now let's take a closer look at these 2 IoT markets. Largely agreed that the consumer Internet of Things consists of home, lifestyle, health, mobility, and retail. It's largely also agreed that the consumer market is centered upon enhancing quality of life and increasing consumer convenience. We've all been exposed to consumer hype, and you've probably made a product purchase as a result of it. Buy this gadget and it'll make you healthier, or buy that gadget and it'll tell your fridge to cool the beer in time for the football game. So now I know why fridges need to talk to my cell phone. But in all seriousness, the hype is endless. Where did the hype originate? Initially, the hype was driven by the carriers themselves to support huge investments they made in infrastructure upgrades required to augment their voice networks with faster, more reliable data transmission capabilities. The goal, once the infrastructure was in place, was to equip everybody with a smart device. You can't watch TV for more than an hour today without seeing a smart device advertisement by a carrier. The devices being introduced all share one thing in common. They are designed to share or access increasing amounts of data, photos, videos, access to the internet. Heck, they're even willing to give the devices away to you as long as you sign that long-term data contract. Once the networks were in place and everybody's got their smart device, it's now the consumer product-oriented companies that are taking over, and they are compounding the hype. Okay, we finally arrived at the industrial Internet of Things. GE coined this phrase just a few years ago. The industrial Internet of Things is defined as a network of things, machines, computers, people, and processes that enables intelligent industrial operations using advanced data analytics. Industrial IoT centers upon the 7 vertical markets that you see here: health, energy, transportation, smart cities, manufacturing, public service, and others. Consumer hype, while annoying to some, it hasn't hurt the industrial side one bit. In fact, it's helped it in 3 significant ways. As I just mentioned, it's resulted in significant cost reductions in every aspect of the industrial Internet of Everything ecosystem, including sensors, controllers, communication, and web-based application services. Secondly, it's raised technology awareness amongst industry leaders across all industrial verticals, which has led to some adaptation, which in turn has led to increased exposure to some pretty fantastic success stories out there that are pure industrial. And lastly, it's resulted in a formidable movement by IoE industry giants to draw a line, segregating the hype of commercial IoT from the substance of industrial IoT. Separating return on investment-based industrial from convenience-based consumer has been a hot agenda topic these past few years. With the recent establishment of the Industrial Internet Consortium a year ago, March, I suspect you will see this trend continue. Consortium membership has exploded in just over a year to 170 member organizations, representing a who's who in this space. Consortium's goal is to address the complexities of the industrial Internet. Handling big data and its security are right at the top of the agenda. The desired end state being faster adaptation, quicker deployments, and transformational business outcomes worldwide. I recommend that you keep an eye on this consortium. Over time, they may very well set the path towards deployment standardizations. Now that we've segregated industrial from smart devices and consumer IoT, there exist 2 additional industrial-related acronyms that require further clarification. The first, they are machine-to-machine communications, or M2M, and Industry 4.0. Starting with M2M, until just recently, it was the industrial acronym. With the acceptance of IIoT as the new acronym, M2M has been relegated to defining a subset of the industrial market. And this makes sense since M2M focuses solely on communication from machine to machine, while industrial IoT expands to include communications between machines and objects, machines and people, and machines and infrastructure. Now moving on to Industry 4.0, I suspect all of you have been exposed to this term and will increasingly be exposed to it. Dr. Chris Bladowski of the Manufacturers Alliance for Productivity and Innovation recently published a paper that breaks down the 5 major differences between the 2. They are as follows. Industry 4.0 originated in Germany and is fully supported by the German government. Industrial IoT comes from the Industrial Internet Consortium. Industry 4.0 has been adopted and is enforced within Germany as a means to maintain a perceived competitive advantage in manufacturing innovation, whereas Industry IoT is all about organizations banding together to establish and share best practices. Industry 4.0 is being called the fourth industrial revolution, focused primarily on manufacturing, whereas industrial IoT stretches across many sectors including manufacturing, energy, healthcare, public services, and transportation. Germany sees its competitive advantage in manufacturing as equipment and hardware driven, whereas the consortium specializes in hardware, software, data processing, and communications. Industry 4.0 is particularly relevant to Germany's small to medium-sized companies. It's internal in scope, and industrial IoT is supported by global multinationals or global in scope. Okay, so Industry 4.0 has been referred to as the Industrial Revolution. As this slide predicts, the revolution centers upon adding cyber-physical systems to all aspects of production and distribution within the manufacturing sector. I would keep an eye on what comes out of Germany in regard to Industry 4.0 because it could in fact also be one of the drivers towards implementation standardizations. Okay, now back to the industrial Internet of Things. Presently, it's a $1 billion device market representing $200 billion in revenue. I believe the vast majority of the industrial IoT devices out there today, likely more than half of the billion, have been around for some time, namely in fleet, trucking, automotive fleets, and on smart utility meters. I believe that industrial IoT will grow exponentially, but not because of these old school deployments in mature markets, but because of innovative deployments across each of the industrial IoT verticals presented back on slide 7. Okay, so let's ask the question, are you ready for industrial IoT? Surprisingly, the answer to that question more often than not is no. Accenture surveyed 1,400 business decision makers from large multinationals, of which 736 were CEOs. 84% believe their organization has the potential. 70%, however, have yet to make any concrete plans or progress. And further, only 7% have actually developed a strategy and assigned resources. This slide summarizes a forecast that suggests that by 2020, industry will spend $514 billion on the industrial internet and its technologies, and in return will receive $1.695 trillion of net value from that spend. That's 149% estimated ROI, and it will come from 5 places: better asset utilization, increased employee productivity, supply chain logistics, innovation, enhanced customer experience, which in the end will result in increased customer orders. Okay, I'm going to move on to present a few success stories in regards to creating new lines of business. A tire manufacturer equips their newest OEM tires with sensors that communicate back to fleet operators and their drivers. The result is fuel savings because of optimal tire pressure. And the next example, a farm equipment manufacturer equips their machines with a full range of sensors that predict maintenance issues before they arise, and that reduces equipment breakdowns, which can obviously be very costly in the middle of a harvest window. And the last example, an engine aircraft manufacturer pretty much followed that same logic as the farm equipment manufacturer, but in this instance, the technology can save lives, not just the wheat crop. The next examples of successful IoT deployments is in the business savings or productivity area. A large beverage bottler replaced all the keyboard inputs in the warehousing, shipping, and service side of their business with voice recognition technology. The results were capital cost savings, increased productivity, and increased customer satisfaction because mistakes were virtually eliminated. And in the last example, a South American bank institution deployed several video cameras, new digital signage, and probably most importantly, a cybersecurity feature for electronic banking. Travel expenses for training went down, wireless bank transactions went up 8-fold, and safety was greatly enhanced. I'm now going to touch upon the Internet, the industrial Internet, and some deployment considerations. Those are highlighted here. It's infrastructure, environment, relationships, and getting started. In regards to your communication infrastructure, it's important that you map that infrastructure, that you plan your migration from field bus to Ethernet to wireless, or including wireless, that you upgrade your network, its bandwidth, memory, switches, and routers. You modify your network design for scalability and security. In regards to the work environment, there are so many things to consider here. You've got decades-old infrastructure and equipment. Is it compatible? Does it need to be replaced? You have extreme conditions potentially, temperature, moisture, noise, vibration. The industrial Internet needs to be built to last. How will all of the existing legacy systems, etc., be integrated? Security, as has been mentioned, is a huge concern. How do you keep your proprietary data secure? Reliable connectivity. Your response to failure, you need a response plan. What will the human-machine interface look like? And where will the various components of your network be placed, including wired, wireless, cable installations, receivers, etc.? Okay, in regards to supplier relations, I imagine that all of you have numerous suppliers. I recommend that you share your ideas and possible plans with all your valued and trusted suppliers, accept their input, but in the end, make your decision only after evaluating all alternatives. There are several non-biased professional services firms out there that can help you with this. They are increasing in number, and they are calling themselves IIoT systems integrators. I believe that a pilot project is important. You have to start off with a real compelling business reason to deploy an IIoT solution. And once you've done that, even if it's the simplest of solutions, and you've placed the connectivity, you understand the component parts, you will find significant other ways to leverage your knowledge and your experience to introduce new and exciting applications and solutions. Quickly, here are the pitfalls that you need to avoid. Many go too big, bite off more than they can chew, especially if it's an 100% internal project without any outside IoT expertise. When you think you have understanding of all the moving parts, revisit each again. Clear objective has to be established right from the get-go. Achieve that, get the system operational, and then take it from there. Make sure you engage all the relevant internal players and departments, even if it's the simplest of projects. Never shortchange your budget. You do this, and when you're halfway finished, your project may die on the vine by the time you convince the release of additional funds. Don't be afraid to ask for help, both internally and externally. Again, a qualified industrial systems integrator is a good place to look. And it's going to take time to get all the pieces of the puzzle in place, from the various sourcing parts to negotiate. You've got the carriers, you've got the applications, you've got integration. My final two slides reiterate a couple of recommendations that I think you will find familiar. And the first is to start with a pilot project. Studies have shown that companies that want to move from simply recognizing the benefits, they actually do something about it. And it's been proven that the earlier adapters are quicker to embark on further projects once they've seen the value IoT brings to that aspect of the business. And finally, the recommendation of engaging a systems integrator. IoT represents a whole new set of challenges. How will your systems be implemented? How will they be deployed? Who will maintain them? These are all questions that a systems integrator can help with. And in closing, I wish you luck as you explore the world of opportunities that the Industrial Internet of Things opens up for you. My contact information is presented below. If you have any questions, please feel free to reach out to me. Thank you, Mark.
Thanks, Mike. I appreciate your input. We have a few time for questions. We have some questions from the registrants and then questions during the presentation. So we'll answer as many as we can. And the audience can continue to type questions in the Ask a Question box on the screen. And then we will post answers to the questions we don't get to along with the archive. So first of all, how important is Ethernet to and IPv6 to IIoT?
This is Mike Richmond. I think they're both really important. They're both being used now in industrial applications. Ethernet we talked a lot about, IPv6 a little bit less, but without IPv6 you would not have the address space, the ability to uniquely identify and address these devices. So it's very, very important that the applications, the gear, the networking protocols, everything that you deploy is capable of using IPv6.
Good. Let's see. The role of wireless networks for sensors, controllers, actuators, and other devices. Mike Peters? Perhaps Mike is not unmuted his phone. All right.
My apologies. The role of wireless networks is what the Industrial Internet of Things is pretty much all about, even though a significant amount of your things will be connected through wires. You need to come up with a wireless strategy, and that strategy requires mapping out your infrastructure, creating lines of sight between receivers and nodes. It requires a pretty decent understanding of wireless communication. And the carriers today have all set up divisions, industrial internet divisions, and they're more than willing to assist, with answering questions and providing some support in terms of mapping out your infrastructure.
Good. And a lot of questions deal with security. Perhaps each of you could provide a little more information about how security will be addressed in the IIoT era.
So this is Mike Richmond. I'll go first. The most important thing that you can do to ensure that your deployments are secure is make sure you have deployments that you can upgrade, that you can update the software. If you stick your head in the sand and say, hey, it's not going to happen to me, I'm not going to let people connect to the internet, I'm going to epoxy up all my USB ports, there's no way. I would just say, ask the Iranians and the people running their centrifuges about how well that works. You have got to have the ability to upgrade your software, or you will not be secure. It's just a matter of time.
And
Mike
again,
Peters, did you want to add?
Yeah. Yes, sure. Again, on the network side, the carrier side, they have set up, and they highly recommend, if information is sensitive, such as water treatment facilities, etc., that you establish a VPN, a virtual private network, to the cloud, and then you host your data internally, which is common, more so than actually on the cloud. The cloud is a conduit through basically your own link.
Right. And you can use cloud software technology in private clouds, which is also a good way of getting the benefits of scaled and agility without having your stuff actually exposed outside.
Great. Thanks so much. We'll get to the other questions offline. Thanks everybody for attending today and for the great questions. I have one extra note. Control Engineering just posted our research page, 6 IoT Industry 4.0 Key Findings, and you might want to take a look at that. The information is on the screen.